All right, we're going to talk about rational functions and their graphs today. This is a really long lesson, so just kind of be warned. If it starts getting too long, we might take it and break it up. But a rational function, remember we talked way back when we first started the class, we talked about how the word rational means fraction. So a rational function is a fraction, and basically you have a polynomial on top and a polynomial in the denominator. That's what we call a rational function. So before we get too much into that, let's just talk about a little bit about some fraction stuff. Right? It says here are some arithmetic properties associated with division. Okay, that can help us understand the behavior associated with rational graphs. So the first one says there is no such thing as a fraction with zero in the denominator. Okay, we've already talked about that, right? Way back when we first started talking about, we said, hey, 5 divided by 0, that doesn't make any sense. It's nonsensical. So we say, right, it's undefined. It doesn't equal anything. So just a heads up on that, just remember you cannot divide by 0. And that's going to be important because we talk about rational functions, you'll have an x in the denominator, which we've done these when we found domain. We talked about how you can't have a 0 in the denominator. So when the numerator of the fraction is considered larger than the denominator, then the quotient will have a large absolute value. Okay, so what it's talking about, if I take, for example, I don't know, 50 and I divide it by 0.01, and you can grab a calculator and do that if you want, right? I think it comes out to be I think it comes out to be 5,000. So when you take a large denominator, or a large numerator, excuse me, the top's large, the bottom's small, and you divide it, you're going to get a large answer back out, right? That came out to be 5,000. And that's going to be helpful to us here in just a second. Now, notice how it says a large absolute value, right? Just like we always do. If you have a negative, if I have a negative 50 divided by 0.01, instead of getting a large positive value, you'll get a large negative value, right? It comes out to be a negative 5,000 when you find that. So keep that in mind. If you divide a number, that's larger than the top's larger than the bottom, you're going to get a large number back, especially if that denominator is less than 1. It's going to cause, whenever you divide by a number less than 1, you get a larger number back again. Next one says, when the denominator of a fraction is considerably larger than the numerator, then the quotient will have a small absolute value. So what's that saying is if I flip that over and I take a really small number like 0.01 and I divide it by 50, right? Instead of getting a really large number, I'm going to get a really small number instead, right? If I go 0.01 divided by 50, by 50, it comes out to be 0.0002. Okay, and the bigger this denominator gets, the closer to 0 it will become, right? The smaller that value will get, and it'll get closer and closer to 0. Now, if I go 0.01 divided by 500, it's going to be 0.0002. We could keep going. It'll keep getting smaller and smaller and smaller. Same thing can happen from the negative side, right? The only difference is if I put a negative up there, it's going to get closer to 0 from the negative side instead of the positive side. Okay, a fraction is equal to 0 if and only if the numerator is equal to 0. And this is important. Right here it says the denominator is a non-zero. So what we mean by that is, 0 divided by 5 equals 0. And really anything, if I have two things divided, the only way it can equal 0, the only way is if a is equal to 0, right? The numerator has to be equal to 0 for that division problem to equal 0. And what it's saying is this, just be careful, 0 over 0 is not 0. Okay, you cannot divide by 0 even if I have a 0 in the numerator. This is still undefined. So just be careful with that. When you have the sign of the numerator is the same as the sign of the denominator, you'll have a positive. Like we know this, right? If I have either 5 over 5, or let's go, I don't know, 5 over 6, or negative 5 over negative 6. If I have two positives or two negatives, it's going to be a positive. Okay. If they have opposite signs, whether it's negative 5 over 6 or 5 over negative 6, right? That just means when you divide them, you're going to end up with a negative answer. Okay. And we know that same signs, right? When you're dividing or multiplying gives you a positive, and opposite signs when you're dividing or multiplying gives you a negative. So all those things are just some really basic stuff that you've all seen before, but that's going to help us as we go through and graph these rational functions. We're going to talk a lot about, if you get a positive or a negative, or hey, my denominator is going to be really big, my numerator is going to be small, like on this problem. What's going to happen? It's going to give me a really small number. Oh, my numerator is really big, my denominator is really small. I get really big numbers back. So all this is going to help us here as we go through and talk about this next part. All right, so without further ado, let's look at a rational function, and we're going to look at some points and see if we can come up with a good sketch of what this one looks like. So my function is h of x equals x minus 2 over x squared minus 9. And it says draw by plotting as many ordered pairs, determine the equation. We're going to do a little bit of we are going to plug it in and get some points, but we're going to do a little bit of base work to make this job a little bit easier for us. All right, we've already talked about the domain of functions. And one thing we said is if you have a fraction, we just talked to it up above, is that it cannot equal 0. So that x squared minus 9 cannot equal 0. So we could factor that. Right, that's a difference of squares. It's x minus 3 times x plus 3. So what would make your denominator equal to 0? Well, I know for my domain is x cannot equal 3 because I get a 0 there, or negative 3 because I get a 0 there. So we've done that before. Now, as it turns out, when you have a rational function, right, and again, this is rational because I have a polynomial on top, x minus 2 is a polynomial, and a polynomial on the bottom, x squared minus 9 is a polynomial. So that's what makes it rational when you're dividing. When you have one of these, whenever you have a restriction on the domain, so in this case, x cannot equal 3 or negative 3, one of two things are going to happen. Either you're going to have a vertical asymptote. We haven't talked about what that is, but we will here in just a second. Or you're going to have a hole in the graph. Okay, one of those two things. Okay, so we're going to try to figure out what happens at negative 3. So we're just going to plug in some values. So one thing we can do, before we get to 3 and negative 3, let's actually find, I want you to do these on all the problems. Let's find the x-intercepts and the y-intercepts. Right? If I want to find an x-intercept, we've talked about this. If I'm on the x-axis, if you look where my cursor is there, if I'm on there, that means y has to equal 0. So what I'm really saying is, when does that function, for what values of x does that function equal 0? Well, remember what we talked about. For a fraction to equal 0, the only way that can happen is if the numerator equals 0. That's it. Right? If you have 0 divided by something, it equals 0. So all I really have to do is say, when does x minus 2 equal 0? And that's pretty easy to solve when x equals 2. So I know that my x-intercept is when x is 2, y is 0. Right? So we got a point right there. Let's put that point on the graph. Okay, y-intercept. Well, for y-intercept, look at my cursor. When we're on the y-axis, that means x has to be 0, right? If it were bigger than 0, I'd be over here. If it's less than 0, I'd be to the left. So that means all I have to do is plug 0 in for x. So I'm saying, what is h of 0? So if I plug 0 in, I get 0 minus 2 over 0 minus 9. That's negative 2 over negative 9. That's a positive 2/9. That's a little hard to graph. We'll just do the best we can. So 2/9, somewhere in that area right there. Okay, we know something's happening at 3 and negative 3, right? Because I've got some restrictions on our domain. There's going to be a vertical asymptote or a hole. Let's see if we can figure out what happens there. So let's go as we get closer to 3. And this is a little tough, right? 3 is right there, right? There's 3. So let's plug in like 2.5 and see if we can figure out what happens. If I plug in 2.5, h of 2.5, I get 2.5 minus 2 is 0.5. And then I get 2.5 squared. Let me grab my calculator here. And we'll figure out what 2.5 squared is. 2.5 squared is 6.25. Okay, I'm going to divide those. So I'm going to go 0.5. Oh, shoot, I got a minus 9. I'm sorry. All right, 2.5 squared minus 9. Okay, when I subtract those, 6.25 minus 9, I end up with negative 2.75. And we can divide those. So 0.5 divided by negative 2.75 equals like 0.18, negative 0.18. So that's a little tough, but again, you know, at 2.5, we're just down there. Let's try something even closer. Let's try like 2.9, and hopefully we see something interesting happen here. I'm gonna maybe jump down here just a little bit. Maybe I'll come up over here so you can see it still. So let's go h of, and let's pick something really close to 3. I know at 3 it doesn't work. We want to pick something really, really close. So if I go 2.9 minus 2, that one is 0.9 divided by 2.9 squared. Let's see, 2.9 squared is 8.41 minus 9. End up with a negative 0.59. So let's divide those. 0.9 divided by negative 0.59 equals a negative 0.31. So that's down just a little bit more. This is, let's see, this is 1 right here. This is super hard to draw, but it's right in there. And what's going to happen as we plug in, like, I could plug in like 2.999 next. What will happen is this number right here will get a little bit bigger, right? If I go 2.9999 minus 2, I'd be 0.999. But this number right here will keep getting smaller and smaller. Well, what will happen then is even though this number is small, this number will get super small. So I have a bigger number divided by a smaller number. Remember what we said, when that happens, when I have a bigger number divided by a smaller number, I get a bigger and bigger answer back out. So what happens if I plug in like 2.99999 all the way in there, I'm going to start getting values down, like way down here. So the graph comes along, and this has what we call a vertical asymptote. So what that means is it cannot equal 3, but as it gets closer to 3, the graph's going to follow that dashed line I drew right there. So it's going to go right along the edge of that. Let me actually do that in a different color. I'm going to change my, so there's my vertical asymptote. You can see it. The graph never gets to 3, but it follows that vertical asymptote and gets closer and closer to it as we get closer to 3. So the graph's just coming right along the edge of that all the way down there. So we'll go through it in just a second. But sometimes, again, when we have these restrictions on the domain x cannot equal 3 or negative 3, again, there's two options. Either it can be it can be a vertical asymptote or a hole in the graph. This one is a vertical asymptote. Same thing happens at negative 3. I'm going to get into why in just a second. And we could plug in a bunch of points to see that, but that takes a really long time. And I'll talk about here in just a minute the difference, like why sometimes there's a hole and why sometimes there's a vertical asymptote. But at both of these places, there's actually a vertical asymptote at 3 and negative 3. Okay, so what's going to happen is this graph, as it comes across, right? I want to get the general shape of it. As I come across, I probably need another point over here somewhere. Let's plug in negative 2 and see what happens. So if I plug in negative 2 on top, I get negative 2 minus negative 2 is negative 4. On the bottom, I get negative 2 squared is 4. 4 minus 9 is, what, a negative 5? The two negatives make it a positive. So it's right there at 4/5, which is pretty close to 1. And what's going to happen is this graph has to go up along this vertical asymptote. And the way I know that is if it went back down, it would have to cross the x-axis again. Well, the problem is there's only one x-intercept. We found it right there. It only crosses right here at 2, 0. So if it doesn't cross again, that means it has to go along here and curve up along that vertical asymptote. So that's one of the reasons why it's so important to find, these are hard to draw, but it's so important to find those, the x-intercepts, because if I know it only crosses in this one place, I'll do it a different color, I'll highlight it. That is my only x-intercept right there. Well, that means as I come this way, right, it can't cross again, so it's got to curve up. And that saves me a lot of time. I have to plug in a lot fewer points. Okay, the last thing we need to talk about is we need to talk about what happens to the function as x gets really big. So remember we talked about end behavior of polynomial graphs. So, they either, as x went to infinity, either y went up to infinity or y went down to negative infinity. Rationals are a little bit different. So just think about what happens here. I'm going to come over here and come up here a little bit. Think about what happens to this graph of h of x, or to the function as I plug in really big numbers. Like we can plug in a few big numbers, right? If I did like h of 10, that's all the way over here. If I plug in 10, I would get 10 minus 2 is 8. 10 squared is 100. 100 minus 9 is 91. No, that's fairly small number. We're down like at 1/10. That's somewhere down here. Let's plug in like 100 and see what happens. If I plug in 100, I get 98. So the top got bigger, but watch what happens to the bottom. Right? 100 squared is 10,000. 10,000 minus 9 would be what? 9,991. So the top got bigger, but the bottom got bigger a lot faster. So that if I plug that in a calculator, let's plug that in there just so you can kind of get a comparison here. If I go 8 divided by 91, that's about 0.08. If I go 98 divided by 9,901, that's 0.009. I think I may have done, 0.009. So it's quite a bit smaller. And what's going to happen is the bigger numbers I plug in for x on here, right, in the denominator, it's going to get bigger faster than the top. And so I'm going to keep getting values out that are closer and closer to 0. So what happens is this graph has what we call a horizontal asymptote. So as I draw, I'll actually do it that same color so we can see the asymptotes. So I can draw the asymptote along there. So that graph is going to get closer and closer to that line. And it turns out, if I go to the left and try the same thing, the exact same thing happens. So it's going to get closer and closer to 0 as I go to the left. So that's our end behavior. Those are called a horizontal asymptote, right? Instead of going vertically, they're running horizontally. So this graph, I know that it comes along here and gets closer right there. So as it comes this way, we could plug in a few more points, but for the most part, I don't mind you just sketching it. I know it has to curve up there along that vertical asymptote because if it went down, there'd have to be an x-intercept right there, and there's not. One thing to be cautious with is sometimes with a vertical asymptote, right, my graph can never cross there because x cannot equal 3. So graphs cannot cross vertical asymptotes. Graphs actually can cross horizontal asymptotes, right? If you draw this horizontal asymptote all the way across, right, it crosses that point in the middle. Horizontal asymptotes only tell us what happened as x gets really big. So as x gets really big, you can see it getting closer on the right. Okay, on the left side though, I don't know if my graph is up here or down here. It's got to be one of those two because it doesn't cross. So let's just plug in a point and see if we can figure it out. So let's pick some point off the side. We did positive 10. Maybe we'll do negative 10. So let's plug in h of negative 10 and see what happens. Okay, so we're plugging it in there. I get negative 10 minus 2 is negative 12. Negative 10 squared is 100. 100 minus 9 is 91. I already knew it was going to get close to 0. That number is a pretty small number. I just wanted to find out if it was negative or positive, and that is a negative. Right? If I divide, let's see if it comes out to be as a decimal. So if I go negative 12 divided by 91, I end up with a negative 0.131. So really, I'm right. I mean, it's really close out here. Okay, but what that tells me is my graph is above over here. So it's going to come in, sorry, I did that. It was supposed to be a negative. I apologize. Let me fix that. It was a negative 0.1, so it's not above. It's below. So right up in there. And what that tells me is because there's no x-intercepts over here, it never crosses the x. That means it has to come along there. And then as it gets to this vertical asymptote, it's going to curve down, go in that direction. So there's a sketch of what that graph would look like. So we're going to kind of go through a list here. I'm going to give you a list of things you can do to check or to find out when you go to graph these, like some steps you can follow. as we go down through this. Let's look at another example. As we go through this, I'll kind of go through it, and then we're going to talk about how you tell if it's a vertical asymptote or a hole, and then we'll go through, like, I call it like my rational expressions graphing recipe. Like if you follow these steps, it makes it a lot easier to graph. So let's look at this one right here. So it says, draw a graph of the function g of x equals x squared minus 9, 2x squared plus 6x by plotting points. We're not just going to plot points because that takes a really long time. So I'm going to show you some shortcuts ways of doing this. So the first thing I would always do, I'm going to put some steps over here. We always want to factor. We want to factor the denominator and the numerator. All right, so factor both the top and the bottom of the fraction. So on this one, we'll talk about y here in just a second. So up on top on this one, we just did that, right? That's a difference of squares. X squared minus 9 is x minus 3 times x plus 3. 2x squared plus 6x. Like, be careful. Remember all our good factoring stuff. You can take a common factor out of there. A lot of times we miss that. So if I take out a 2x, that would leave me with what? X plus 3. So that's our first step, is to factor the denominator and the numerator. Okay, number 2 is state the domain. So find the domain. Well, if we have it factored, it's easy to find the domain, because all we have to do is look at the denominator. What would make it equal to 0? Okay, well, when would that 2x equal 0? That'd be if x equals 0. So we know x cannot equal 0 because of the 2x there. When would x plus 3 equal 0? When x is negative 3. Okay, so I know x cannot equal 0 and x cannot equal negative 3. Okay, this is really important to know that 0 and negative 3 will be one of two things. Either it will give you a hole in the graph when x equals 0, or it'll give you a vertical asymptote. So they both, one or the other could be a hole, one or the other could be a vertical asymptote. So the way we do that, the way we figure out which is which, is we want to reduce the fraction if possible. What I mean by that is we want to see if there's a common factor. So if I come back over to g of x, if you look up here, that x plus 3 and that x plus 3 reduces. So what that leaves me with is x minus 3 over 2x. Now, in reality, they're not quite equal, because on this one, I can plug in negative 3, right? There's no x plus 3 on the bottom. I can plug in negative 3 over here. On this one, I can't. So off to the side. So as long as x does not equal negative 3, they're equal. They're the same. Okay, so step number 4 is find the holes and the vertical asymptote. And they go to, you do them in the same step, and I'll tell you why. So find the holes and the vertical asymptotes. Okay, so here's how we do it. These are my two candidates. 0 and negative 3 will be my holes and my vertical asymptotes. Okay, so the way I tell is I look at the reduced form. Anything that still gives me a 0 in the reduced form is a vertical asymptote. So if you look right here, I still have a 2x there. That means if I plug 0 in, I'd still get a 0 on the bottom of the fraction. So on this one, we would say x equals 0 is a vertical asymptote. Okay, so if you want to make a little note here, vertical asymptote is, you look at the reduced function. Right, I reduce that fraction, and I look at what's left over, which was the 2x. That tells me that that is a vertical asymptote. Okay, the holes. The holes will be any factor that reduces completely, that disappears. So factors that, I'm going to say reduce out. And what I mean by that right here is like that x plus 3 and x plus 3 is gone. So over here, there's no x plus 3 on the bottom. So that means that negative 3 is going to be a hole in the graph. And we can actually figure out where that hole is. So this is important. If you watch here really quick, I know there's a hole when x is -3, and there's a vertical asymptote at x equals 0. So at -3, what I can do is I can plug -3 into my reduced fraction up here and see what I get back out. And that will tell me where the y value is of my point where the hole is. So if I plug -3 and I get -3 minus 3, I'm going to do it up here, is -6. 2 times -3 is -6. -6 divided by -6 is 1. So there is a hole in the graph at -3, 1. Okay, we're going to take those two and put that information on here. So we know that there's a vertical asymptote at x equals 0. So it's kind of hard to see. I'm doing it in a different color. Hopefully it shows up, right? So that's right, x equals 0. That's right along that y-axis going along there. But there's also a hole at -3, 1. So if I go, -3 is right there, right? And 1, this is going by 5s. So 1 would be right here. So right there, I'm going to draw an open dot. There's a hole right there. Okay, the next thing we're going to do, so far we have factored the numerator and denominator, found our domain, and those two things will either be the holes or vertical asymptotes of 0 and the -3. We reduce the fraction. Anything that reduces out, the x plus 3, whatever went with that, which was the -3, that's a hole in the graph. Okay, whatever is left over, like that 2x in the denominator, that gave us a 0, so 0 is the vertical asymptote. Okay, I'm going to erase that bottom part. Make sure if you need to pause and write that down, you can. I'm just going to erase the factors describing how to get a hole and how to get a vertical asymptote, just so we have more room. So go ahead and pause it and write that down if you need to. Okay, so step number 5. So step number 5 is we're going to find the horizontal asymptotes. So do the horizontal asymptotes, which is really, it's really just the end behavior of the graph. Okay, I'm going to show you a shortcut way of doing this too. So we're going through a lot here in this problem. Once we go through this the first time, it'll be a lot faster on the other examples. So to determine the end behavior, you could plug in a bunch of points and see what happens. But it's a lot easier to do these little shortcuts. And what we do is we compare, so this is how we find the horizontal asymptotes of the end behavior. We compare the degree of the numerator and the denominator. Okay, and there's 3 different cases. Case number 1 is if the degree of the numerator is less than the degree of the denominator, then it's like that last problem. You're going to have a horizontal asymptote at y equals 0. The second possibility is if you compare the degree of the numerator and the denominator and they're equal. Okay, what you do is you just set up a fraction. I'm going to call it a over b, but a and b are just the leading coefficients. And I'll show you what that looks like. This problem actually is an example of that, and I'll show you what that looks like. So the a over b is the leading coefficients. If you want to write off to the side of a and b, they're the leading coefficients. Okay, the next option is number 3, is if the numerator is greater than the denominator. Okay, then there is not a horizontal asymptote, so there's no horizontal asymptote. Now there is a possibility that there is what's called a slant asymptote, and our last example actually has one of those, so I'm going to show that to you. I'm going to save that, that for when we go through that last example though, okay? So here's what we're talking about. So come back up to the problem, and it actually doesn't matter what form you look in, right? We have all these different forms. We have it up here, the original form, when it was all expanded. We have this factored form. We had this reduced form. You can compare any of them. For the horizontal, I think a lot of times it's easier to compare just the top and the bottom. So remember, the degree is just the highest power. So the highest power on that one is a 2, and the highest power on that one is a 2. So that's what I'm comparing, is just those 2 terms. And the reason why is this: as x gets really big, this minus 9 doesn't really matter, right? If I plug in small numbers, 5 squared is 25, minus 9, it makes a big difference. Let's say I plug like 100 in. 100 squared is 10,000. Minus 9, the minus 9 doesn't really matter. If I plugged in like a million squared minus 9, the minus 9 kind of becomes insignificant. Same with even the 6x. That squared gives you such big numbers that this 6x doesn't even really matter. Okay, so I compare the degrees. This one's degree 2, and that one's degree 2. So that's our second case down here, right? The numerator equals the denominator. All I do is take those leading coefficients. So what I mean by that is take what's in front of the x squared on top. That's a 1x squared. And take what's in front of the x squared on the bottom. That's a 2. And what that means is I'm going to have I'm going to put it down here. I'm just going to abbreviate the horizontal asymptote at y equals, and I'm just going to go 1 over 2. I just took the number in front of the x squared, the number in front of the x squared, so 1 over 2. So if I come down to my graph, that horizontal asymptote is true going to the right and to the left. So going to the right, it's going to get closer and closer to a half as it goes out. Going to the left, it gets closer and closer to a half as it goes out. Now remember, it can cross that horizontal asymptote, but as it goes out, it has to get closer to that. Okay, we're really close here. The last thing, let me zoom out a little bit here. The last thing we're going to do on our curve sketching recipe is number 6, is we're going to find the x and y intercepts. So add that to your list. So we're going to find the x and the y intercepts. So remember, to find the x-intercept, you plug 0 in for x and find y. That was the y-intercept, sorry. For the y-intercept, you plug 0 in for x and find y. Let's put that over there, actually. So to find the y-intercept, we plug 0 in for x and find y. For the x, you plug 0 in for y and find x. Okay, so if I go back up there, if I plug 0 in for y, I'm going up to the side here, I get 0 equals x squared minus 9 over 2x squared plus 6x. And that doesn't look fun to solve, but remember what we talked about. The only way this fraction can equal 0 is if the top can equal 0. So I'm going to go x squared minus 9 equals 0. We already know that factors to be x minus 3 and x plus 3. So the only time that top fraction could equal 0 is at positive 3 and negative 3. But there's a problem with one of those. Up here, we said in the domain x cannot equal negative 3. So negative 3, when I plug it in, I get a 0 on top and I get a 0 on the bottom. Okay, that cannot work. It's undefined. So I actually have one x-intercept. So I'm going to come up here. I have an x-intercept at 3, 0. Okay, let's find the y-intercept. For the y-intercept, we just plug 0 in for x. So I get 0 minus 9 over 0 plus 0. Hey, didn't I say up here x could not equal 0? Right, I get a 0 on the bottom of the fraction. So this one actually does not have a y-intercept. So let's write that down. No. And I guess we already knew that if I'd been paying attention, right? Because we have a vertical asymptote when x is 0 along there. Okay, and then from there, this list is long. Whoops, sorry about that. From there, we are going to just plug in points as needed. Plug in numbers for x. I'm going to reword that. I'm just going to say find points. So we're going to plug some numbers in for x and find some points. Now, interesting enough, let's add what we have, though. So I've got the, let's come back over here and look at all our information. I've got the vertical asymptote drawn. I've got the horizontal asymptote drawn. I have the hole in the graph. We haven't put our x-intercept on there yet. So let's go ahead and put our x-intercept. It's at 3, 0. Now, I can already tell what the right side of my graph looks like. Remember, it has to get closer to a 1/2. So as I go up this way, it's got to be getting closer to a 1/2. That's hard to draw because I don't have much room there. It's getting closer to a 1/2. And then it has to cross. If we want to, we could plug in 2 just to see what we get. If I plug in 2, let's do g of 2 just to get another point there. 2 squared is 4. 4 minus 9 is a negative 5. let's see, 2 squared is 4, times 2 is 8, 6 times 2 is 12. So I think I got, you can double check that. I think a negative 1/4. So we're down here somewhere. So that graph is coming over and curving. And then I know there's a vertical asymptote. I don't need any more points. I know it's going to curve down along there, right? It's going to follow that vertical asymptote going that direction. Okay, over on the opposite side, I know that there's a hole in the graph where I drew that. I don't need any more points because there's no x-intercept, so it doesn't cross the x-axis. So it's going to come along this at a half. Whoops, that should be right above there. Sorry, it's hard to draw. It's going to hit that hole. It skips that point, and then it's got a curve. It's going to curve up along that vertical line. Now, if you wanted to plug in -2 or -1 and get some more points, you could. I'm not as worried about that. I just want you to do as many points as you need to so that you can get a good sketch of what the graph looks like. I know this example is long. This is going to be a long video. The main thing is this. It should go a little bit faster now that we have these recipes, these steps to follow. Make sure, take just a second if you need to pause the video. Make sure you have those 7 things written down. If you do those 7 things each time, then that helps us to organize everything. And then when you're done, you have a lot of information about the graph, and we just have to put it all together and try to draw a sketch of what it looks like. So if you need to pause it, write down those steps, and then we'll do a couple more examples where we'll go through all of them. Okay, now here's a summary of some of the stuff we already talked about. Most of this, so we can make this fast, but it says, when working with a rational function, we can find useful information about the properties of the graph by factoring and finding input values that cause division by 0. So that's really saying, like that part right there, the factoring and finding input values that cause division, you're finding the domain. We know that the function will be undefined at those values, but we need to determine if it's a hole, right? Our choice is a hole in the curve, or if there's a vertical asymptote. So, right, if it's a hole, here's a little trick, is if the top and the bottom come out to be 0, so the top and the bottom are both 0, then it's always a hole, okay? So a hole in the graph, let's just circle that here. A hole in the graph will always get 0 on both the numerator and the denominator. If it's a vertical asymptote, then you'll get usually, at least in the reduced form, you'll get a 0 on top, but you'll get a 0 on the bottom, but not on top. So if you, at the very beginning, if you do have a 0 on the top and the bottom, you know automatically that it's a hole in the graph. Okay. Other than that, we're just following the exact same steps we just did. So let's run through those steps again. Here's a new problem. We have f of x equals x squared minus 9 over x squared minus 2x minus 3. Right? And it says pay special attention to the behavior of the graph at -1 and 3. That's kind of giving us a hint there. Let's go ahead though, right? First thing we said is to factor it. So let's write it in its factored form. F of x equals, that top part, we factored that several times. It's the difference of squares. The bottom, that's a trinomial, right? It's x and x, minus 3 plus 1. Okay, now don't get confused with the top. The domain, we don't care about the top. We just want to look what makes the bottom equal to 0. So domain, we'll put it up here above maybe. The domain is x cannot equal, let's say it could not equal 3, right? 3 minus 3 is 0. And it cannot equal a -1. So it can't equal 3 or -1. Now those could either be holes in the graph or they could be vertical asymptotes. So let's reduce it. The x minus 3 and the x minus 3 just reduce. So when I reduce it, I end up with x plus 3 over x plus 1. That's its reduced form, as long as x does not equal 3. Now watch what happens if I plug 3 in, right? 3 minus 3 is 0. 3 minus 3 is 0. 0 times something is 0. And we end up with a 0 on the top and the bottom, right? So 3 is a hole in the graph. So remember what we set up above. The x minus 3, because it reduces out completely, it's gone over here. That means it's a hole in the graph. So I'm going to put that down. We'll write all our information. Maybe I'll write it up here above. Maybe I'll put it over here on the left side. So we know that there's a hole in the graph at when x is 3. And if you want to find out, we want to find out exactly where it's at. So we need to know the y coordinate. I can plug 3 in back over here. So if I plug 3 in, I get 3 plus 3 is 9 on top. And 3 plus 1 is 4. So I get 9/4. Oh, geez, sorry. 3 plus 3 is not 9. Sorry about that. Just took the easiest math and screwed it up. Let me try that again. Okay, so 3 plus 3 is 6, and 3 plus 1 is 4, so 6 fourths. That's 3 halves or 1.5. So let's put that on my graph. If I come over to 3 and up to 1.5, there's a hole in the graph right there. We're just going to draw a hole right at that point. Okay, if you look at -1, after I reduced it, right, here's my reduced form, it still can't equal -1. That means it's a vertical asymptote. So a -1, which is right here, let's do it a different color just so it stands out and you can see it. There's a vertical asymptote going up and down there. Okay, so we got the domain, we reduced the function, we found the vertical asymptotes. Next thing we're going to do is the horizontal asymptotes. Once you get used to this one, it's a really easy one. All we do is look at the original problem. The degree of the top is 2, like my highest power is a 2. The degree of the bottom is a 2. My highest power is a 2, so they're the same. So I just take the numbers in front, right? So what's in front of the 2, and it's always the leading coefficients, the highest power. So that's a 1x squared and a 1x squared. So that means I have a horizontal asymptote at y equals 1, because I take the 1 over the 1. Oh, I never wrote down my vertical asymptote. I have a vertical asymptote at x equals -1. Remember, vertical lines, equations of lines are always x equals, horizontal equations are always y equals. So let's go ahead and draw that. So I know at 1, as it goes out, it's going to be getting closer to there. And if you want to, you don't even have to draw those the horizontal asymptotes all the way across, because it only follows it as I go to the right and to the left, okay, as the graph goes out. Okay, let's see, next thing on our list. So we found the horizontal asymptote, right? Look at our list up here. Next thing is the x and the y intercepts, and then we'll plug in some points if needed. So let's do the x and the y intercepts. So we're going to plug, and you can either use, you have a choice. You can either use the original equation, or it's even easier if you want to, we can use the reduced equation over here. That's fine. So if I use that one, f equals x plus 3 over x plus 1. But just remember, x cannot equal 3, right? Because over here on the original problem, it couldn't equal 3. Okay, so to find the y-intercept, you plug 0 in. I plug 0 in, I get, for x, I get 0 plus 3 is 3, 0 plus 1 is 1. So I know that there's a y-intercept, plug 0 for x and got 1 out for y. Okay, and then do the opposite, plug 0 in for y and solve for x. Well, if you look at this, remember it's a fraction. The only way a fraction can equal 0 is if the top equals 0. If x plus 3 equals 0. So that would be at, well, when x is -3, right? Go, when does x plus 3 equal 0? When x is -3. So for the x-intercept, it's going to be x is -3 and y is 0. Okay, let's take all this information and see if we have enough. If we do, great, we will graph it. If not, we'll plug in some more points. So we got the hole, we got the vertical asymptote, we have the horizontal asymptote. There's a y-intercept at 0, 1. Okay, right there. And there's an x-intercept at -3, 0. So there's a point right there. Okay, to the left is pretty easy. This has to come along here. Has to come along here. Has to hit that point, cross the x-axis. So I wasn't drawing that very good. It should be above, just coming along that horizontal asymptote. It has an x-intercept, and that means it has to go down along here. Okay, and that's just from following, following my, see if I can do a little better job of that part right there. Okay, so it's going down along there. This is a little bit trickier over here, right? But there is no x-intercept. If there's not an x-intercept, it cannot cross on the right side. That means it has to come from this side, right? Because there's no x-intercept. So it's come down and hit that point, and then it curves back up, hits that point, and then it's going to come down along there. Now, if you want to get more exact, we could plug some numbers in. Like we could plug 1 in and see what happens. If I plug 1 in, I get what? -8. So So I'm going to go h of 1. I get -8. Or we can just plug it in here. That's even easier. Let's do that. You can plug it in the reduced form. Let me try that again. Oops. Sorry about that. So if I plug in -1 over here, I get -1 plus 3 is 2, and -1 plus 1, or sorry, +1 is what we're plugging in. 1 plus 3 is 4. All right, we're going to plug in 1 right there and see what I get right there. And 1 plus 1 is 2, so that's 2. So actually, it's all the way back up to here. So it does something like this, where it comes down, hits that point, curves back up, and then it's just going to curve back around and come and go out that direction. Let me just erase that inside part. So there might be a place here and there where you have to plug in a point. My curve wasn't very good. This should be a smooth curve, but it's coming up like, there we go. That's a little bit better. And then it's curving down and following along that horizontal asymptote. So it should look something like that. Just a warning, you're fine. Like, I have no problem. You need to know how to do this without a calculator, but I have no problem when you're done. If you want to get your graphing calculator out or go to Desmos and draw a sketch of it, you'll be able to see the vertical asymptote. You should see the horizontal asymptote. It won't show the dashed lines, but you'll see where the curve follows it. One thing you won't see, just kind of a heads up, is their calculators are not good about showing holes in the graph, because basically calculators just find points and connect the dots, and so they don't recognize holes. So just know your hole in the graph will not show up if you're checking your answer on a graphing calculator. Okay, nothing new here. We're just going to do another example. We'll go through another one. We've already talked about there being a hole. Talked about vertical asymptotes. Okay, this is the only new one. Remember I said if the degree of the top is 1 more than the degree of the bottom. So here's some examples. Look down here. The degree of the top of this one is 3. That one is 2. So the degree is 1 more than the bottom. Whenever that happens, right, so I'm going to underline this right here. Whenever the numerator is greater by exactly 1 degree than the denominator, we have what's called an oblique asymptote. What that really means, write this above here, oblique really means a slant. So instead of having a horizontal asymptote as the graph goes out, there'll be like a slanted asymptote as the graph goes out. So here's another example, right? If that one's degree 8, that one's degree 7, the top's 1 more than the bottom, so that means it has a slant asymptote. Okay, so just remember, all you're comparing the degree of the numerator to the degree of the denominator. If the top's smaller than the bottom, it's always going to be just y equals 0. It goes along the x-axis. If they're equal, like the last two examples we did, then you take their leading coefficients and it will have a horizontal asymptote that approaches those lines. You'll see an example of an oblique asymptote here in just a moment. Not this one, but the next one. Okay, we're going to go through the exact same steps that we just did. So we'll see if we can make it a little bit faster now that we've done it a bunch. We want to factor the top and the bottom. So this one's a little trickier to factor, but that top part is just the difference of squares, right? I got 2x squared minus 3 squared. So it factors to be 2x minus 3 and 2x plus 3. The denominator, that's a trinomial, so we do our 2 sets of parentheses. 2x squared is going to be 2x and x. Factors of 3, I think it has to be the 3 there and the 1 there. We can check that. Right, if I times, that would be 2x and 3x, which adds up to be 5x. So I think we're good. We've got it factored. Okay, let's find our domain. So my domain, what can x not equal? Well, we only look at the bottom of the fraction. I have a 2x plus 3 and an x plus 1. So when does 2x plus 3 equal 0? Because we don't want it to, right? Minus the 3 over, divide by 2. So x cannot equal -3/2. So my domain, we know that x can't equal a -3/2. So that's either going to be a hole in the graph or that's going to be a vertical asymptote. Okay, the other one is x plus 1. That's a little easier, right? -1 plus 1 would equal 0. So x cannot equal -1. So -3/2 and -1 will either be holes in the graph or vertical asymptotes. Each one has to be one or the other. Okay, the way we check that is the next step is where's the vertical asymptotes, where's the holes, is see what reduces. Well, I have a 2x plus 3 and a 2x plus 3, so that reduces to be 2x minus 3 over x plus 1. Now remember, we know that x cannot equal negative 3 halves still, right? Because in the original problem, we'd get 0 over 0 if that happened. But what that tells us is it tells us which one's a hole and which one's a vertical asymptote. So when I look at the reduced form, x can still not equal negative 1. That means it's a vertical asymptote. So I have a vertical asymptote at x equals negative 1. The hole in the graph then is the one that reduced. Well, the negative 3 halves came from the 2x plus 3's. So since they reduced, that means that's a hole in the graph. So there's a hole in the graph at negative 3 halves. But I want to find the y coordinate, so we need to plug negative 3 halves in here and see what we get. This will be a little bit trickier because of the fraction, but I'm going to do it off to the side over here. I go 2 times negative 3 halves minus 3. Those twos, that's 2 over 1. Those twos just reduce. I have negative 3 minus 3, so I get a negative 6 on top. On the bottom, I go negative 3 halves plus 1. That's negative 1.5 plus 1. That's negative 1 half. Divide both. The two negatives make it a positive. 6 divided by a half, that's the same as timesing by 2. So I think we end up with 12 right there. Okay, got my first 3 steps down. Found the domain. I've factored the top and the bottom, found my domain, found my vertical asymptote, found my hull. Okay, let's do end behavior. So we're going to look at, for end behavior, we're looking at comparing the degree of the top and the bottom. I think it's easier to look at the original problem up here when we do that. Hey, they're both x squareds. That means that there's going to be a horizontal asymptote at y equals, and I just take the leading coefficients. I have 4 over 2. Well, that's really just y equals 2. So that's where a horizontal asymptote is. Let's find our x-intercepts and our y-intercepts. For the x-intercept, you just plug 0 in for y. I'm going to use this reduced form right here. So I end up with 0 equals 2x minus 3 over x plus 1. Well, again, a fraction equals 0. That can only happen if the top equals 0. So when does 2x minus 3 equal 0? We can solve that. 2x minus 3 equals 0. I add the 3 over and divide by 2. So 3 halves, 1.5. Okay, let's find the y-intercept. So this time I plug 0 in for x. That's a little easier. Again, we can plug it into this reduced form. So I get 0 minus 3 over 0 plus 1. So I plug 0 and I get negative 3 over 1, which is negative 3. Okay, now we've got all this information. We are going to go back. Let me kind of erase some of this stuff out of the middle. If you need to pause and write it down, go ahead and do it. So I'm going to erase some of this work. Okay, I'm just going to take it and we're going to take all this information I have up until now, put it on our graph, and then we'll decide at that point what we want to do, like if we need to do some more points or not. Okay. So I'm going to start with my asymptotes. I know there's a vertical asymptote of negative 1.5 or negative 3 halves. That's somewhere along there. There's a hole in the graph. Sorry, I did that wrong. The vertical asymptote was at x equals negative 1, wasn't it? Let me try that again. So at x equals negative 1, which would be there. There's a vertical asymptote. There's a hole in the graph at negative 3 halves 12. We'll see, that's 1.5 and 12, so we're all the way up. Somewhere right in there, there's a hole in the graph. Okay, we know that there's a horizontal asymptote at x equals 2. And again, that's just as you go out. We don't care what happens in the middle, but as I go out, I know that graph has to get closer to 2 as I go out that way. We have a y-intercept at 1.5, 0. So 1.5, that's somewhere right in there. And that's my only x-intercept. So we probably have enough to graph this. We got our y-intercept, sorry, at 0, negative 3. So over here, right, it's got to come in along that vertical asymptote and hit those 2 points, and then it's got to go along that horizontal asymptote. So that's what my right side has to look like, something like that. Okay, over here on the left side, it never crosses the x-axis. So that means it's just coming along here. It has to hit that hole in the graph. And then it's going to be curving up that way. So we don't have to, I mean, if you want to plug in some more points, we could plug in -4 or -3 and get some more points. I'm not looking for that though. The main thing I want you to have is all those things, all those steps that we did, right? Domain, the holes, the vertical asymptotes, the horizontal asymptotes, the end behavior. Okay, the x-intercepts, the y-intercepts, and then if you need points, do more points. But if you have a general shape of the graph, you're good to go at that point. Okay, we got 2 more examples, guys. I know this is a super long lesson. This is why we're breaking it up over 2 days. If you need to pause and finish it, finish it later or tomorrow, go ahead and do that. Just make sure you have a fresh brain. Stick with me through these last 2 examples. Okay. Oops, sorry about that. Okay, so determine all the asymptotes, holes, intercepts of the graph of the function, then plot it, the points to get a graph of the function. Okay, so let's go through our steps. So let's go ahead and factor it first. That would be x minus 1 over on the bottom. You could factor out an x. That would leave you with x squared minus 1. Well, x squared minus 1 is the difference of squares, so we can factor it again. Okay, so we got our factored form. So let's do our domain. Okay, be careful. Don't forget that x. If I plug 0 in there, I get a 0 on the bottom. So x cannot equal 0, 1, or -1. Okay, so those are my possible holes or vertical asymptotes. Now we're going to reduce it. Oh, I forgot the -1 on top. Sorry, it's x minus 1 on top. Now we're going to reduce it and see what we have left over. So that x minus 1 and that x minus 1 reduces. That leaves me with a 1 on top. That's what I'm left with. Remember, whatever still makes it equal to 0, whatever factors are left are vertical asymptotes. So I'm going to have a vertical asymptote at x equals, I still have the x, so at x equals 0. And at x equals, I still have -1 would still give me a 0. Okay, so there's my 2 vertical asymptotes. The x minus 1 reduced out completely. So that means at 1, when x equals 1, there's a hole in the graph. And I want to figure out what that hole is, so let's plug 1 back in here. I get, what, 1 over 1, 1 plus 1, that's 2, so a half. Okay, so I got my vertical asymptotes and my holes in the graph. Let's do end behavior next. So my horizontal asymptotes, I'll put it over here. This is a pretty easy one. The degree of the top is 1. The degree of the bottom is 3. So what's going to happen is the bottom is going to get bigger a lot faster than the top. When we have big numbers on the bottom and small numbers on top, it gets closer to 0. So this is just going to be y equals 0. That's my horizontal asymptote. Okay, let's do x and y intercepts. So let's do the y-intercept first. For the y-intercept, just plug 0 in for x. I'm going to plug it into the reduced form. You can do either one, though. Oh, we can't actually, right? Didn't we say x cannot equal 0? So there is no y-intercept. So no y-intercept, right? Because we said you cannot plug 0 in for x. Let's find the x-intercept. To do the x-intercept, you plug 0 in for y. So I would get 0 equals 1 over. Well, here's a problem. Remember, for this to equal 0, the top has to equal 0. So when does 1 equal 0? Never. So there's no y-intercept. Or no x-intercept, sorry, or a y-intercept. So we don't have either of those two. We're probably going to have to plug in some points here. I don't think we'll have enough because we don't have the x and the y-intercept to kind of guide us. We'll see, though. Okay, let's take all that information. I'll make it as big as I can here, and we'll try to graph it. So let's do a different color for the vertical asymptotes. I got one at 0. X equals 0. That's just along the y-axis there. We got one at x equals -1. So those are pretty close together. Okay, so there's my vertical asymptotes. We have a hole in the graph at 1.5. So let's, for the actual graph, I'll go back and we'll go to 1.5. That's kind of hard to graph, but right there, we have a hole in the graph. Okay, and then we have a horizontal asymptote at y equals 0. So as I come closer, as I go out to the right, it gets closer to 0. And as I go out to the left, It's closer to 0. Okay, well, this, I probably have enough information over here. There is no x-intercept over here, and my hole is above. So I think I know the graph has to be above over here. It's got to come along that vertical asymptote. It's got to hit that hole, and then it's got to go out along that horizontal asymptote, getting closer and closer to it. Over here on the left side, I'm not sure what happens. Let's plug in a number. So let's go back up to our function again, and you can use the reduced form. We can use the 1 over x times x plus 1, as long as, right, as long as I don't plug in, just make sure we don't plug in, what did we reduce that? We don't plug in a positive 1. Okay, so let's plug in like, should we do like -4? What is f of -4? That'd be 1 over, I got -4 times -4 plus 1 is -3. That's 1/12. Right, that'd be a positive on the bottom. So I get out to -4, it's above. It's really small, but it is above. Well, that's enough. I don't need any more info because I know it's above now. So it's got to go through that point. It's got to curve up along this vertical asymptote, going that way, and it's getting close to that horizontal asymptote going that direction. Okay, we are not done though, because between 1 and 0, the graph's going to exist, right? There's a domain between there, right? We can plug x values in as long as I don't, between 0 and -1. So I'm going to pick a number somewhere between there. I need to figure out, it's either going to come this way, if you see my cursor there, or be down below going that way. So let's plug in a half. That isn't the funnest number, but I think we got to plug something in between. So I think that's what we're going to have to work with. A half times a half plus 1 is 1.5 or 3 halves. Times those together. What's that? 3/4. That ends up being 4/3. So at 1/2, I'm up somewhere. What's 1 1/3? Somewhere up in that area. And that graph means it has to come along that vertical asymptote. This is hard to see. See if we can zoom in on that a little bit. All right, I found that 1 point, so it's got to be going up on either side, going that way. All right, this is a process, and it's going to be a process as you go down through this. It takes a bit. Okay, hey, we just crossed an hour. This is long. Sorry. We have one more example though. So let's get through this last example. This is going to have that oblique asymptote, and then you guys will be good to go. So it says determine all the asymptotes, holes, intercepts, same thing as before. There's my function. Let's follow our steps. Remember our recipe. Number 1, we want to factor the top and the bottom. So I get what? X plus 2 and x plus 1 on top. On the bottom, we get x minus 2. Okay, what's my domain? Well, ignore the top. It's what makes the bottom equal to 0. So x cannot equal 2. So my domain. Okay, next thing is decide on a hole or vertical asymptote. We only have one value just when x is 2. Well, does x minus 2 reduce? Well, I have an x plus 2, but that does not reduce with x minus 2. So this does not reduce. That means the x minus 2 does not go away. That means it's a vertical asymptote. So we have a vertical asymptote at x equals 2. There is no hole in the graph. Let's do horizontal asymptotes. This is a tricky one. So on the top is 1 bigger than the bottom, right? That degree of the top is 2. The degree of the bottom is 1. So when that happens, what that means is that there's a slant asymptote. And the way you find a slant asymptote, you guys are going to be excited, is we get to do long division or synthetic division. I'm going to do long division just to remind us how to do that. But we just take the x minus 2. You could do synthetic if you wanted to. That's fine. We're going to take the x minus 2 and divide it into x squared plus 3x plus 2. All right, so what do I times x by to get x squared? Or I can go x squared divided by x. That's just x. X times x. X times a minus 2. Subtract them. That would be 0, 5x plus 2. Okay, what do I times x by to get 5x? Positive 5. 5 times x. 5 times a minus 2. Make sure you subtract them. Change the signs. And end up with 12. So remember, there's a plus 12 over x minus 2. Okay. Here's kind of the cool thing. That looks messy. But this part, that 12 over x minus 2, remember, we're thinking about what happens as x gets really big. Well, the bottom's going to get bigger and bigger and the 12 stays the same, right? If I plug in like a million down there, a million minus 2, if I take 12 divided by that, it's going to be a tiny number. So as x gets really big, this part's kind of insignificant. You never have to worry about the remainder. So what happens is, as this graph goes out, I'm going to put this down, it has an oblique asymptote. An oblique asymptote. The rest in there. And it follows the line y equals x plus 5. And I'll show you what that looks like in just a second. Before we do that, let's find the x-intercepts and the y-intercepts. Okay, for the x-intercept, we plug 0 in for a y. Okay, so remember, for a fraction equals 0, the top has to equal 0. So that would be when x equals, there's an x-intercept on that one, right? Would be when x equals -2. And on this one would be when x equals -1. Okay. For the y-intercept, we're going to plug 0 in for x. So if I plug 0 in for x, let's see, we get 0 plus 2 times 0 plus 1 over 0 minus 2. So that would be 2 times 1 is 2 divided by -2. So I think we get -1 there. Okay, let's take all this info, put it on the graph, and see if this is enough to come up. If not, we'll use some points in addition to it. So we know there's a vertical asymptote at x equals 2. So at x equals 2, we're going to do a vertical asymptote. There's no hole in the graph, so we don't have to worry about that. Okay, my oblique asymptote, the way we draw that is I graph the line y equals x plus 5. So this is this is going back to stuff you've already learned in previous math classes. But that just means it crosses at 5, and the slope is 1, right? 1 over 1. So from there, I'm going to go, we got to be careful with our scale. 1 is actually, this is 1 right there, right? So I got to go up 1 and over 1. Do the same thing. You can go up 1 and over 1. So if I draw that horizontal line, right, that's what we call it a slant asymptote or oblique asymptote. It's because it slants across there. So these are kind of cool. So let's start putting our points on there. I have an x-intercept at -2, 0 right there. And then I have another one at -1, 0, which is right there. And I have a y-intercept at 0, -1. Okay. So this left side over here, that kind of shows us what happens. It has to come along that slant asymptote. It's going to hit those points. And then since I'm down here, it can't go back up because it doesn't cross the x-axis, so it's going to go down along that vertical asymptote, go in that direction. Now I got to figure out, is my graph up here or down here? Well, if it were down here, like if I tried drawing it down here, it would have to cross the x-axis, right? It doesn't. There's no x-intercept over there, so it can't be down there. So what that means is that it's got to be up here in this corner up here. Okay, go in that direction. So that's what our graph is going to end up looking like. Okay, this is a long assignment. There's a lot to it. There's a lot of information here. Make sure as you go through the assignment, come back here and look at the examples. I tried to show you some examples that were pretty similar to the ones that the examples on here are pretty similar to the ones you'll have in your assignment. So make sure you refer back to this, and then make sure you keep track of your questions, because when I get back with you, we're just going to go through questions from this assignment. That's all we're going to do. We're not going to go through a new lesson. Anyway, good luck, guys.